Alright, so the next routing protocol we're going to talk about is Eigrp. Eigrp is it's a classless routing protocol, much like OSPF. It allows VLSM, just like OSPF. It's referred to as a hybrid routing protocol, or, in my opinion, more accurately, an enhanced distance vector protocol. Again, OSPF relies on a distance and a next hop. It relies on information to be summarized by its neighbors to it, so it's pretty much a distance vector protocol. It does perform auto-summarization, but it also allows for manual summarization. This is one of the unique features about Eigrp. It is Cisco proprietary though, so you better have all Cisco equipment if you want to be running Eigrp in your network. There is much less overhead with Eigrp than OSPF, and because of the triggered updates, Eigrp is a very, very fast convergence, typically sub-second. Now, Eigrp has a relationship much like an OSPF adjacency in that Eigrp routers need to become neighbors. There's requirements for this neighbor relationship, much like there are requirements for adjacency in OSPF. You need to have the same authentication, you need to have the same autonomous system number. This is a new concept. You need to be in the same subnet, which makes sense. I mean, ideally, if they're connected to the same network, they should be in the same subnet, but there are some times where you can configure two devices that communicate that do not have the same subnet mask, and so it's very important. Now, the routers actually check up on this. And then Eigrp needs to send hellos for discovery and heap alive. And this is actually done with a different protocol than OSPF, but it's very similar in fashion. So hellos are done for Eigrp discovery, and then to keep the connection alive once Eigrp neighbors come up. After the routers become neighbors, a full topology exchange is performed. So once the routers exchange that information, then a full topology exchange is performed, and after that point, only partial updates are needed. So you don't have to send a full link state database just like you did with OSPF. It's only going to exchange the updates that are required. And the route is actually chosen based on a simple metric, and we'll be talking about that metric here in a bit. Now, Eigrp cost is a little bit more complex than OSPF, and here you can see the full form of the equation. Now, you don't actually need to know this for the CCNA, but I wanted to give you an idea of how it's calculated. So, Eigrp cost is determined very similarly to OSPF in that there is a least bandwidth component. There is an inverse of least bandwidth. Now, in the case of OSPF, it would add the cost on each link. With Eigrp, it actually looks at the lowest bandwidth over the entire path and uses that as its least bandwidth parameter. It's also going to take the delay on each link and add that up, so it will use the least bandwidth and cumulative delay. Now, the bandwidth is in kbps, cumulative delay is measured in tens of microseconds, and so here are some defaults. You can play around with these numbers and actually calculate what some of the associated costs are. Now, there's some weird Eigrp terminology that you need to be familiar with because the routing process is a little bit different. There's what's called feasible distance, and this is going to be the cost of the best route to reach a given subnet. We have also what's called the reported distance, and this is going to be the distance reported upstream by the router's neighbor who gave them the route for the feasible distance. And so the successor is going to be the route that succeeds. The successor is the route with the best metric to a given network, and that metric is going to be the feasible distance. The feasible successor is an alternative route that's based on the following criteria. If a route's reported distance is less than the current feasible distance, then it gets installed as a feasible successor. So a feasible successor is basically going to be a backup route, but it has to meet that requirement. Eigrp actually supports unequal cost load balancing, and OSPF only supports equal cost load balancing, but Eigrp, you can set a specific variance, and it will actually load balance based on the variance. So the metric difference to install two routes is called the variance. If the route is greater than variance times closest route, it will not be installed and it will not load balance. And load balancing will be performed based on the cost of the route. So if one link is 2 times as good as the other one, it will send 2 packets over that link and then 1 packet over the other and then 2 packets on that link and back and forth in that fashion. Now, the maximum number of routes installed can also be configured directly. We'll talk about these commands here. So router Eigrp. Now you'll notice instead of an OSPF where we just had process ID, here this number after the router Eigrp actually reflects what's called the autonomous system number. And so this autonomous system number needs to match, if you'll recall, between all routers that are configured in the same Eigrp cluster. And so the idea here is that Eigrp is performed within a single autonomous system. Now, your OSPF process IDs can be whatever you want them to be, and they can be different on every single router in your network. As long as the areas are the same and the other authentication and timers are the same, it'll work fine. But with Eigrp, you need to make sure that you have these two routers in the same autonomous system. You can add networks very similarly as you do in OSPF with a network, the network address and the wildcard. Again, not a subnet mask, but a wildcard. You can also specify the maximum number of paths to load balance over and the variance for which you can do unequal cost load balancing. Now, to apply Eigrp on the interface, you can manipulate the bandwidth or delay, which are both used for the OSPF cost, or pardon me, for the Eigrp cost, as we saw earlier. And then we can also manipulate the hello interval and hold time for Eigrp. Now, for authentication in Eigrp, it works a little bit differently. You have to do what's called a keychain. The idea behind a keychain is that keychains have a number of keys on them. And so you'll give your keychain a name, and then give your keys, each one of your keys, a number. That key string will be affected, and then it'll have an accept lifetime and a send lifetime under which that key is sent. And so what happens is, as time progresses, they'll go through different keys on this keychain. So you won't want to configure just one key on your keychain. You'll have 3 or 4. And as time goes on, you'll switch these keys out and you'll rotate between these keys based on the accept lifetime and the send lifetime. Now, these keys are applied through Eigrp with the following commands, and you'll notice they're applied on the interface. It's IP authentication mode Eigrp, and then the autonomous system number, and then the hash type, so in this case MD5, and then we have IP authentication keychain Eigrp1, and then the name of the keychain that you want to use. Now, keychains, like I said, allow for different keys at different times. You can configure this. I would highly recommend it if you're going to use authentication with Eigrp, but it's a pretty cool feature that's not very commonly known about in iOS. So to monitor Eigrp, we're going to use show IP route, show IP protocols. There are a number of different show IP Eigrp commands that you should be familiar with, as well as the debug Eigrp and debug IP Eigrp commands that will come in handy for real-time monitoring. Again, that wraps it up for Eigrp, and again, I would encourage you to read the book on this. Eigrp is a huge routing protocol with a number of different technicalities that you should be aware of for the CCNA. I encourage you, again, go through, read the book, do some labs, get some examples, ask me questions in person, and then if you have any questions or comments about this video, leave them in the comment section below. Thanks very much.